In this last video, we're going to go over a new technique of integration, which is integrating with respect to y instead of respect to x. So in example 5, we're going to find the area of the region bounded by the graphs x equals 3 minus y squared and y equals x subtract 1. So notice that the second one is given just in kind of normal notation that we would see where the y is isolated. So I get y equals x minus 1, but the first one is given x as a function of y. So x is a function of y. This is a parabola in y instead of a parabola in x. So it's essentially shifted 3 units to the right, which is where the vertex is, and then it's concave kind of left, I suppose you could call it. So if you just tilt your head sideways, you can kind of see what this looks like, but we've got our vertex here at 3, 0, and so this is the equation x equals 3 subtract y squared. And what we can figure out is that if I try to take my sections perpendicular to the x-axis, two important things happen. So one important thing is that the top function changes at some point. And we dealt with something like that in the last example, so no big deal. We can deal with that. We would just have to write two different integrals. It does get rather complicated though, because when the function changes here, we have kind of the top half of a square root function and the bottom half of a square root function, and we're basically going to have two separate integrals. I should actually color code this so you can see that it's a different type of rectangle when I'm here, and the point where it's going to change is right here. So if I am to the left of that yellow point, the top function is going to be the line, and the bottom function is going to be the negative root function. Notice this is a parabola, but if I write it y in terms of x, it would be a square root. And then if I'm to the right of this yellow point, I'm going to have a top half that is the positive root and the bottom half that is the negative root. It's not impossible, it just would be very, very messy. And of course, we will still do it the messy way so that you can see that you get the same answer. But instead of doing this as two separate integrals with respect to x, we're going to do it as a single integral with respect to y. And the way we're going to do that is we are going to draw our representative rectangles perpendicular to the y-axis. Now you don't have to do an actual rectangle. Again, we're using the limit definition of the integral as a way to conceptualize what's going on, but we're not actually doing the limit definition. So if you'd like, you can just draw a straight line. What we really need to do is we need to find this quantity, which we're going to call the height, and then this quantity is going to be the width, which instead of calling delta x, we would call delta y, and that is going to turn into the dy when we actually do our integral. So hopefully you can see, and maybe you turn your head sideways, that the top function actually turns into being the right. So top becomes right in this context, and the bottom function in this context becomes the left function. So my top function or my right function is this parabola, and my bottom function or my left function is this line. One thing we do need to do is reorganize this line equation so that it is a function of y instead of a function of x. And that's pretty easy to do. If we just solve for x, we get x equals y plus 1. So if we are going to calculate our height, our representative heights are going to be found by taking the top function, which is 3 minus y squared, subtract the bottom function, which is y plus 1. So top function or right function, bottom function or left function, and that is going to be the height of my rectangle. So let's go ahead and go to the next slide, and the integral should be set up for us there. So this is exactly what I wrote down. What I didn't clarify was the bounds of the integral. So let's talk about the bounds. So again, this is the top function, which is this parabola, and this is the bottom function, which is this line. Now we're integrating with respect to y, because remember, when we're talking about our representative rectangle, this would have been delta y had we been doing it the limit definition way, and that delta y is what becomes the dy in the integral. The bounds of integration are going to be y values. So we are scanning and doing our rectangles up like this. So let's draw a few more rectangles on there. They might look something like this. But we are going to be integrating with respect to y. That means we need to be choosing, instead of the x's, we need to be choosing the y coordinates of the points of intersection. And just to show how we could find those, we would just set the functions equal to each other. So 3 subtract y squared equals y plus 1. Move everything to one side, so I get y squared plus y subtract 2. I go ahead and I factor that, and it should be y plus 2, y subtract 1. So I get y equals -2 or y equals +1. So this ordered pair got kind of covered up here, but we're looking not at the x coordinates, we're looking at the y coordinates. So that's why my bounds of integration are based off of the y values there. Okay, at this point, we could, if we want to, go ahead and simplify the integrand. So our integrand is -y squared subtract y plus 2. We're integrating with respect to y. Other than setting this up, nothing's really different when we integrate with respect to y. So we're just finding an antiderivative, just with the y variable instead. Now this may look familiar to you because I think we've gotten a very similar example before. We end up plugging in the top number first, so I have -1/3 subtract 1/2 plus 2, and then I have 8/3 subtract 2. Subtract 4, and this is actually exactly what we've had before. This ends up being 9/2 if you just plug everything in. So in the end, we just ended up integrating a polynomial function. We set it up with respect to y for the ease of setting up the integral. I was able to use just a single integral with a top function and a bottom function. So on the next example, we are going to do this the long way, which is integrating with respect to x. So same example, same functions, but now we're going to integrate with respect to x. And as I discussed at the beginning, this is going to be a little bit longer because this is going to require two separate integrals. The first thing that we need to do is we need to convert this x minus 3y squared into a y equals. So I get y squared is 3 subtract x, and then y is the plus or minus square root of 3 subtract x. And you'll notice here that I did two different colors because we have a top and a bottom. The plus is the top one. So this is y equals the positive root of 3 subtract x, and then this is y equals the negative root of 3 subtract x. So now I'm integrating with respect to x. So what I need to do is I need to figure out where I switch integrals. And I did that in yellow before, so I'll go ahead and do it in yellow again. So this is where I'm going to switch from one function being the top to a different function being the top. So if I'm starting here, now I'm integrating with respect to x because my widths, you can see, are delta x's. So I'm going to integrate from x equals -1, so that's right here, until x equals 2, and that's right here. And the function that is on the top is the line, and the line has the equation x minus 1. And the function that is on the bottom is the negative root function, dx. And then I'm going to integrate again from x equals 2 until right here. So this is where I'm going to stop, which is at x equals 3. And in this case, the top function is now the positive square root function, and the bottom function is the negative square root function. So that's just the setup, and on the next screen we'll have these functions simplified, and then we'll actually start integrating. So we have our two integrals set up. So our integral from -1 to 2, x minus 1, the line, and then the root function. And remember, we subtracted a negative, so that became positive. And then we have our second integral that's set up to go from 2 until 3. So the first part of this first integral is fairly straightforward. It is just a reverse product rule. So we're going to have x squared over 2 subtract x, and we're going to evaluate that at the endpoints. The second part, we need to do a u substitution just on the square root. So we're going to do u is 3 minus x, du is negative dx, and we do need to change that integral over to reflect the new bounds. So when I put 2 into this function, 3 minus 2, I get 1. So my top bound is now 1. And when I put -1 in, 3 subtract -1 is 4. And we have negative u to the 1/2 du. So now we're going to go ahead and do that antiderivative. So we're going to add 1 to the exponent, which is going to make it u to the 3/2, divide by the exponent, which is equivalent to multiplying by 2/3, and then we have that negative. But notice the bounds on this integral are different than the bounds on this first one that I had here. Okay, and I'm realizing, oh, I can't erase this now. Oh well. So let's go over here and finish our arithmetic. So we're going to plug everything in. So I'm plugging in 2 into this function. So 2 squared is 4, over 2 is 2. Subtract 2, which is 0. And then I have -1 squared, which is 1, so this is 1/2, plus 1. Okay, and that gives me -3/2. But we're not done yet. That was just this part. We still need to do this part that I've called b. So in the part that I called b, we have -2/3. I'm going to rewrite this as radical u cubed, and we're evaluating over the interval 4 to 1. We don't have to switch this backwards. We just need to make sure that we put the top number in first. So this would be -2/3 root of 1 cubed, and it's going to be subtract a negative or plus 2/3 root of 4 cubed. So that's going to end up being -2/3 plus square root of 4 is 2, 2 cubed is 8, so this is 16/3, and added together I end up with 14/3. And then I just need to combine those two answers together. So -9/6 plus 28/6 is 19/6. So 19/6 is the first part when I've split this up into two different regions. Okay, now I need to do the second part. The second part shouldn't be too tricky though, because we've already dealt with the u substitution and changing the bounds and everything up here. So this will be, we'll need to change our bounds. -2 integral u to the 1/2 du, but now we're plugging these different bounds into our u substitution. So 3 subtract 3 is 0. And 3 subtract 2 is 1. So I end up with -2. I'm going to add 1 to the exponent, so u to the 3/2. I'm going to multiply by 2/3, but I am going to evaluate this from 1 to 0. So if I put 0 in first, I get 0. So I'm going to subtract a negative, so it's going to be plus 4/3 square root of 1 cubed, and I realize right here this should be a 2, and so I end up with just 4/3. Now remember, our answer that we got for this when we did it before was 9/2. So we're going to take those two answers, 19/6 plus 4/3, which is 19/6 plus 8/6, which is 27/6. We're getting there. Reduce a factor of 3, you get 9/2, and it checks. Now, why did I show you this? I showed you this because there is an elegant way to do this problem, and there is a very inelegant way to do this problem. So the elegant way to do this problem was to do my integration. Ooh, I've got a lightsaber here. Do my integration with respect to y. So do my slices horizontally instead of vertically. And when I do it horizontally, there are two main advantages. One is that the function that is the top function stays consistent the entire time, as does the bottom function. So it only requires one integral. The second advantage is when I do this horizontally, this is just a parabola, and I just need a regular old polynomial power rule in order to find the antiderivative. When I did this the inelegant way, I had a top function that switched partway through my region of integration. So two integrals, which just means a whole lot more calculations. So look at all of the calculations I had to do here. And then the second disadvantage to doing this with respect to x is that the bottom function now, instead of just a polynomial function, involves square roots. And requires u substitution and just is generally more complicated. In the end, both give me the same answer of 9/2, but there was clearly an easier way to do this problem. So coming up next, after this, we will start talking about volumes. And the reason I have been bringing up this limit definition of the integral in these videos, we could have done without it, is it's going to be really important to understand that definition when we interpret volumes. So that will be the next section, or section 7.2.